Hello, everyone. I am Ahmed Shukri from Penn State University. I'm delighted to present our work at Deployable Quantum Access Point Selection Algorithm for Large-Scale Localization. This is a joint work with Professor Mustafa Youssef from the American University in Cairo. So the current state of location tracking systems is that GPS does not work indoors. Propagation models do not provide a good accuracy, especially indoors. And finally, fingerprinting systems can provide high accuracy in both indoors and outdoors. But however, as you know, fingerprinting techniques work in two phases. The first phase is offline phase, where we collect the received signal strength measurements from different access points in the environment at different known locations. And then in the online phase, a user stands at unknown locations, scanning his received signal strength measurements. And we compare the online received signal strength vector with the offline stored in the fingerprint, and the closest location in the signal space is reported as the estimated location. So fingerprinting localization has some challenges. One of them is that it does not scale to a worldwide scale. This, of course, because the data storage space overhead, we cannot store large vectors of a large number of access points. And again, the problem of the matching processing overhead, we cannot match a very large vectors of access points. So, and if we try to reduce the number of access points using classical fingerprinting techniques, using classical access point selection technique, the classical access point selection algorithm is usually computationally expensive itself. So our contribution is that we introduce a quantum access point selection algorithm for a larger scale localization. This, of course, enables us to reduce the storage space overhead, reduce the running time overhead, and improve the robustness of the localization systems. We deploy our algorithm on real quantum machine, which is the D-Wave systems, and we deploy our algorithm in a real environment. So a quick overview about quantum computation is that it is a new field on the intersection of physics, mathematics, and computer science. It leverages phenomena of quantum mechanics. Nowadays, one might expect that quantum computation would be the mainstream technology within years. So the basic unit of information is a qubit. It can have various physical implementations like polarization of photons or electron spin. But unlike classical bits, which can exist in one of two states, either 0 or 1, qubits can exist in a superpositioning state of both 0 and 1 at the same time. But when you try to measure it, when you try to know its state, a qubit immediately jumps to either 0 or 1, losing its superpositioning state. QUBO problem is a quadratic unconstrained binary optimization. Like this one, we try to minimize an objective function like f of x, subject to or it has two terms. The first term is Qij, which represents the quadratic coefficients, and Pi represents the coefficients of linear term, and Xij or the vector of x represents a binary variable, either 0 or 1. Why do we care about QUBO optimization problem? Because nowadays most quantum solvers need to convert the problem into the QUBO problem if you want the quantum solver to work on it to find the best solution or the optimal solution. So quantum annealing finds the optimal solution of the problem involving a large number of solutions. It takes the advantages of quantum properties like quantum tunneling, where we can jump from a minimum to another minimum and can find the optimal solution faster than classical. So our basic idea is to select access points with high importance and low redundancy. And by importance, we mean that the access points that have highest influence on the estimated location. We model the importance as a Kramer V measurements. And for the redundancy, we need to minimize the number of access points that have a high dependency on each other. And for the redundancy, we used Pearson correlation. So our QUBO formulation, we formulate our problem as a QUBO optimization problem where we need to find a binary variables x. If this x is 0, this means that the access point is not selected, and if this value is 1, means that the access point is selected. And this access point, this objective function tries to maximize the importance I and minimize the redundancy Rij between two access point I and j. But of course, if we try to maximize the importance, we end up with selecting all access points. And if we try to minimize the redundancy, this ends up with selecting no access point at all. So to strike the balance between importance and redundancy, we use another parameter, which is alpha, and alpha tries to balance the importance and redundancy, which is represented in the two terms here, alpha summation of the importance and 1 minus alpha summation of the redundancy Rxij. So we implement our algorithm on quantum machine D-wave systems with 5,000 qubit. We use the problem of floor estimation as our case study, and we use a building that has five floors and cover an area of 110 meters squared. Of course, we have a number of access points is 520, and the number of samples is 10K. So this figure represents a comparison between the classical access point selection algorithm and our quantum access point selection algorithm. You can see that our quantum access point selection algorithm is faster than the classical access point selection algorithm with more than order of magnitude faster. Okay, so our conclusion is that we introduce a quantum access point selection algorithm for large-scale localization. This results in reduce the storage space overhead, reduce the running time overhead, and improve the robustness of the system. We deploy our quantum algorithm on a real quantum machine and deploy it in a real environment. Our experiments show that we can select fewer than 14% of the available access point, and we still get the same accuracy as using the entire set of access points. And our quantum algorithm has a superior accuracy over the utilization of reduced dataset by classical access point selection counterpart. Our quantum algorithm achieves more than order of magnitude speed up over the corresponding classical counterparts. Thank you.